Morning students, let us start today's class with some problems based on Rolle's law. Okay, what is Rolle's law? All of you know what is a Rolle's law. In a mixture of two volatile liquids, the partial pressure of a component is directly proportional to its mole fraction, and we know its mathematical expression. Partial pressure of A, suppose A is the one component in the mixture. Partial pressure of A equal to P0A into XA, where XA is the mole fraction of that component A and P0A it's a vapor pressure of pure vapor component. Okay, vapor pressure of pure component, that is why P0A. Okay, so here the heptane, first problem, heptane and octane form an ideal solution at 373 Kelvin. Okay, the vapor pressure of the two liquids are 105.2 kilopascal, which is the unit of pressure, and 46.8 kilopascal respectively. What will be the vapor pressure of a mixture of 26 gram heptane and 35 gram of octane? So what is the question? We have to calculate. A solution is prepared by mixing heptane and octane. Okay, so we have to calculate the total pressure of that mixture using the Rolle's law relationships. Okay, so first we know, according to Rolle's law, I already told you, generally PA equal to P0A into XA, where A is the one component, right? So here octane, we can write in terms of octane, partial pressure of octane equal to vapor pressure of pure octane, that is P0 octane into X octane, means what? Mole fraction of octane. So same thing for P heptane equal to P0 heptane into X heptane. Okay, so for calculating the mole fraction means number of moles of that component. For example, here for mole fraction of octane means number of moles of octane divided by total number of moles, that is number of moles of octane plus number of moles of heptane. So first we have to calculate the mole fraction of each one. So we know for calculating the mole fraction we have to know the molecular mass, number of moles, etc. So here first I am calculating the molecular mass of octane. Octane means it is, oct means 8 and it is octane means CnH2n plus 2, right? The hydrocarbon alkane. So its molecular formula is C8H18. So how we can calculate 8 into 12 plus 12 means 1 carbon, 8 atomic mass. Okay, so here 8 carbon, so 8 into 12 plus 1 into 18 equal to 114 gram per mole is the molecular mass of octane. Then molecular mass of heptane, hep means 7 carbon atoms, so C7H16 is its molecular formula. So we can calculate 7 carbon, so 7 into 12 plus 16 hydrogen, so 1 into 16 equal to 100 gram per mole. Okay, so using this one we can calculate first what, before going to mole fraction we have to know the number of moles, then only we can calculate the molecular mass, right? So number of moles of octane, number of moles of octane equal to, so here I am considering octane as which one? B. Okay, so number of moles of octane equal to weight of, or directly you can write number of moles of N, number of moles of octane equal to weight of octane divided by molecular mass of octane, that is weight of octane divided by, just I wrote for octane, okay, molecular mass of octane. So mass of octane is given in the problem, how much it is? 35 gram. Okay, so divided by molecular mass, just now we calculate what is that, it is 114. So what is it? 0.31 moles. So number of moles of octane we got 0.31 moles. Next same thing, number of moles of heptane equal to weight of heptane, WH heptane full you have to write, it is given in the notes. Okay, W, weight of heptane divided by molecular mass of heptane, that is weight of heptane, it is given in the problem 26 gram divided by its molecular mass, just now we calculate 100. Okay, so 0.26 moles. So number of moles of octane also, number of moles of heptane also we got. Okay, so in substituting the mole fraction equation mole fraction of octane, x octane equal to number of moles of octane divided by number of moles of octane plus number of moles of heptane. We know mole fraction equal to what? Number of moles of that particular component divided by total number of moles. Okay. So here octane divided by octane plus heptane. Okay. So here we know octane already we calculated and kept 0.31 moles divided by 0.31 plus heptane 0.26 moles. So total so what is the mole fraction of octane? That is 0.544 is the mole fraction of octane. So it is easy to calculate the mole fraction of heptane. How? We know mole fraction, the sum of mole fraction of two components, that is XA plus XB equal to 1, we know. Okay. So here already we got one component. So mole fraction of octane plus mole fraction of heptane equal to 1. Okay. So here mole fraction of heptane can I calculate equal to 1 minus mole fraction of octane. We know mole fraction of two components equal to 1. Here what are the two components? Octane plus heptane. So x octane plus x heptane equal to 1. Okay. X octane plus x heptane equal to 1. So x heptane equal to 1 minus x octane. Okay. So 1 minus, here already x octane we calculated and kept 0.544, that is equal to 0.456. Okay. So what is the question? We have to get the total pressure. We have to calculate the total pressure of these two liquids, mixing these two liquids. Okay. So here pressure of octane equal to, that is partial pressure of octane plus partial pressure of heptane. We will get the pressure of the total pressure of the solution. So partial pressure of octane equal to this equation according to Rolle's law, partial pressure of octane equal to P0 octane into X octane. Okay. So P0 is given here, vapor pressure of the pure component of octane in the problem, it is given 46.8 kilopascal. Okay. So P0 equal to P0 of octane equal to 46.8 into, what is our mole fraction? We already calculated and kept for octane, which is 0.4544, that is equal to 25.46. Here it is 25.46. Same way we can calculate the partial pressure of heptane. Partial pressure of heptane equal to vapor pressure of pure heptane into mole fraction. Here it is given, what is the partial pressure of pure heptane? It is given 105.2. Here it is given. Okay. Into its mole fraction we calculated 0.456. What is the answer? 47.97. So we know P total equal to P octane plus P heptane. So P octane is how much it is given. We calculated how much it is, 25.46 plus P heptane is equal to 47.97. So what is the answer? 73.43. What is the unit of pressure? Because it's everything is given in kilopascal. So we have to write it kilopascal. So that is the answer. Actually the problems are easy, but the question they are asked, everything will be given. But we have to understand what is the question. Okay. So question will be lengthy, but the solution will be easy. So clear all of you the problem for calculating the total pressure of the solution. Problem is 100 gram liquid A having molecular mass 140 gram per mole was dissolved in 1000 gram of liquid B with molecular mass 180 gram per mole. The vapor pressure of pure liquid B, that is P0B, was found to be 500 torr. Torr means it is the unit of pressure. Okay. Calculate the vapor pressure of pure liquid, that is P0A we have to calculate, and its partial vapor pressure, that is PA, we have to calculate in the solution. If the total vapor pressure of the solution is 475 torr, that is P total, it is given, it is 475. Okay. So first we will start with the number of moles calculation. So number of moles of A equal to mass of A divided by mass of liquid A divided by its molecular mass. It is given in the problem mass of liquid A is 100 and its molecular mass is 140. So we will get 0.71 for 14 mole. Then number of moles of liquid B equal to mass of B divided by molecular mass. Its mass it is given in the problem 1000 gram divided by its molecular mass is given 180. So 5.556 mole. Now we will calculate the number of mole fraction of XB using these values. Mole fraction of liquid B. XB equal to, we know, NB divided by Na plus NB. N equal to number of moles of B divided by Na number of moles of A plus number of moles of B. So substituting, we already know calculated 5.556 divided by 5.556 plus 0.714 equal to 0.886 is the mole fraction of B, that is XB. Okay, so XB we got. Then we know according to Rolle's law, partial pressure of B equal to vapor pressure of its pure component into mole fraction, that is XB. So here it is given P0B is given, here it is given vapor pressure of pure liquid B, that is P0B is given 500 torr into mole fraction, just now we calculated 0.886, that is equal to 443 torr is the PB. PB means what? Partial pressure of B liquid B. Okay. Then we know P total equal to PA plus PB. Total vapor pressure equal to partial pressure of A plus partial pressure of B. So from that we can calculate easily PA value. PA equal to P total minus PB. P total is given 475 minus PB, just now we calculated 443. So what is the answer? PA 32. So we got PA. PA we got, that is 32 torr is the unit. Okay. Then next we have to calculate P0A. Okay. We know XB we calculated. We know XA plus XB equal to 1. So easily we can calculate XA. XA equal to 1 minus XB. So 1 minus XB we know 0.886 equal to 0.114. So we got XA also. So the answer for that we can calculate using the relation PA equal to P0A XA. In this, what we have to calculate? P0A. So P0A equal to PA divided by XA. PA we calculate 32 divided by XA we calculated 0.114. That is equal to 280.7 torr. Okay. So clear all of you this problem. Okay. First we have to calculate the mole fraction or number of moles. Based on that we can do the further calculations. Some more problems are given in the classwork. Okay, notes given in the notes, you can work out that, you can practice that one. Okay, next is very important topic, that is ideal and non-ideal solution, compulsory 3-mark question. Okay, so a solution, that is a binary solution. Binary solution means containing two components, right? Okay, a binary solution containing two volatile components is divided into, volatile means they are vaporizing. Okay, so a binary solution containing two volatile components are classified into ideal solutions and non-ideal solutions. Okay, so we have to know what are ideal solution. Ideal solution means a solution that obeys Rolle's law at all range of concentration of components and temperature. Okay, so ideal solution means that solution that obey which one? Rolle's law at all range of concentration of components and temperature is known as which one? Rolle's law. Which one? Ideal solution. So ideal solution means which obey Rolle's law. Clear? Okay. So in the, what are the characteristics of ideal solution? They will ask what are the characteristics of ideal solution. So ideal solution means their delta V mixing equal to 0. Delta V mixing equal to 0. What is the meaning of that? Means when this formation of this ideal solution, there is no change in the volume takes place. That means suppose the component A is 10 ml and the component B is 10 ml. So after mixing it will be equal to 20, not more than 20, and it is less than 20, not more than 20 and less than 20. That means delta V mixing, after formation of this ideal solution, there is no change in the volume. That is delta V mixing equal to 0. Next is delta H mixing equal to 0. That means there is no enthalpy change is taking place in the formation of ideal solution. Okay, so it's obey Rolle's law. What is the first characteristic? It obey Rolle's law. Ideal solution obey Rolle's law. And the second thing is delta V mixing equal to 0. Here it is given V solution, volume of the solution. After mixing we will get the solution equal to volume of A plus volume of B. Okay, then delta H mixing equal to 0. So that is the three characteristics of properties of ideal solution. Clear? It obey Rolle's law. It delta V mixing equal to 0 and delta H mixing equal to 0. So in this type of solution, we know solution is formed by mixing the solute and solvent. Suppose the solvent is A, we can consider as A and solute as B. Okay. So the force of the interaction between the attractive force between solvent A and solute B in the solution will be equal to the solute-solute interaction and solvent-solvent interaction. That means solution is formed by mixing A and B. So there is an attractive force between the solute and solvent. That is AB force of attraction in the solution will be equal to the BB in solute and AA in solvent. That means the attractive force between all these things are all solute and solvent, and inside the solution the solvent solute will be same. That is the ideal solution. So clear, it is written here solvent A, solute. That is, there is a force of attraction will be there when a solution is formed. A, B attractive force will be equal to BB and AA attractive force. In case of which one? Ideal solution. Example for ideal solution. You have to learn all the examples because they will give the example and they will ask which type of solution it is. Okay. So example for ideal solution is benzene and toluene, normal hexane and normal heptane, chlorobenzene and bromobenzene, ethylene bromide and ethylene chloride, then carbon tetrachloride and silicon tetrachloride, then ethyl bromide and ethyl iodide. These are the examples for which one? Ideal solution. Next, how we can graphically represent an ideal solution. Graphical representation also important. They will ask draw the graph for ideal solution. Okay. So the same graph, this which one, Rolle's law graph, it was I explained in last class. Same graph we can follow for ideal solution because the ideal solution means they obey Rolle's law, right? So here it is mole fraction in this axis and here it is which one? Vp means vapor pressure. You have to write vapor pressure here. Okay. So here you can see XA equal to 1, XB equal to 0. That means here the mole fraction of component A is 1. Okay. And B is 0. Here B is not there. Okay. And here P0A means what? It is the vapor pressure of pure component, A, component A. Okay. Vapor pressure of the pure component A. That means here only XA is there. That means A component is there. Its vapor pressure P0A. So XB is increasing. Mole fraction XB is increasing means what? Here you can see XB equal to 1. It was 0. Here it's become 1 and XA equal to 0. So this here you can see P0B. That means the vapor pressure of the pure component B only here. Okay. So here we can see it was in the beginning XA is the maximum, mole fraction of A was maximum, so it is having the pure vapor pressure here. It will keep on decrease. Okay. Here you can see in the beginning XB was 0, so there is no P0B and it will be, if there is no partial pressure of B, so it will be like this increasing. Okay. So this line represents the partial pressure of A and this line represents which one? The partial pressure of B, and this line represents the total pressure. Total pressure equal to partial pressure of A plus partial pressure of B. Okay. So P total equal to PA plus PB. So that is the graphical representation of ideal solution. So what is ideal solution? A solution that obey Rolle's law at all range of concentration of component is known as which one? Ideal solution. Clear? Next is non-ideal solution. What is non-ideal solution? The solution which does not obey Rolle's law at all range of concentration and temperature is known as what? Non-ideal solution. Okay. So the solution which does not obey Rolle's law at all range concentration of component and temperature is known as what? Non-ideal solution. Okay. So there are two types of non-ideal solutions are there. Non-ideal solutions with the positive deviation and non-ideal solution with the negative deviation. So how we can write the characteristics of a non-ideal solution is here. We can see here non-ideal solution means these things will be changed. Non-ideal solution, here delta H mixing not equal to 0. In ideal it was equal to 0. Delta V mixing not equal to 0. That means volume of the solution may be higher than or lower than the components A and B. Okay, so it does not obey. What are the characteristics of non-ideal solution? It does not obey Rolle's law at all range of concentration and temperature. Okay, so here delta H mixing not equal to 0 and delta V mixing not equal to 0. So there are two types of non-ideal solutions. Non-ideal solution with the positive deviation and non-ideal solution with the negative deviation. So clear this ideal solution and its graphical representation and characteristics. Next is non-ideal solution. We know non-ideal solutions are two types. So non-ideal solution with the positive deviation and non-ideal solution with the negative deviation. So first is non-ideal solution with the positive deviation. Okay. So in this case, in this type of solutions, the total vapor pressure of the solution will be greater than that of an ideal solution with the same composition. Okay, so with Rolle's law, for example, a solution containing 20% water and simply I am telling 20% water and 80% ethanol. Okay, so according to Rolle's law, they calculated and kept its vapor pressure. Okay, but the vapor pressure is higher than that of the ideal solution with the same composition. That means as per calculation how much more than that will be expected. Okay, more than that will be we are getting. Okay, so that type of solutions are known as what? Non-ideal solution with positive deviation. That means the solution which have the total vapor pressure is higher than that of an ideal solution of same composition. Okay, so that is known as non-ideal solution with the positive deviation. So in this case, what is happening is, we know in ideal solution, the A-B interaction, that in solution, that means solvent-solute interaction in the solution was equal to solute-solute and solvent-solvent, that is BB and AA interaction. But in this case, what is happening is the in solution, the solvent A and B, solvent A and solute B interaction or attractive forces are weaker than solvent and solute attractive or interactant force. What is here? In this case, the solvent solute interaction in solution is weaker than the solute and solvent interaction. So it is weaker in solution compared to when the solute when it was in pure state and the solvent when it was in the pure state. Compared to that, when they form the solution, the attractive forces will become weaker. So what will happen? It is weaker, so it is very easy to escape from liquid phase to which state? Vapor phase. So more vapors will be produced. That is why the pressure of the vapors will be more. Okay, so the vapor pressure will be increased. So what is the thing in this case? Why it is having more vapor pressure is in this case the solution, the interactive force between A, B will be weaker than that of the pure components A and BB. So that is why it is very easy to break the bond and they will convert to which state? Vapor state. So that is why the vapor pressure will be more compared to the ideal solution with same composition. Okay, so next what here? So we know here, so the weaker interactive force between A and B in the solution. So it is the molecules AB molecules are A and B are loosely held in the solution. A and B are, because it is weak, so A and B are loosely held, and that is why the intermolecular distance between A and B will be larger. That leads to what? The increasing volume and also the increasing enthalpy. Okay, so what is happening? It is weaker. AB force of attraction is weaker in case of which one? In this type of non-ideal positive solutions. So it is weaker means what? They are loosely held. Okay, so loosely held means the intermolecular distance will be more. That is why when this type of solutions are forming, the volume will be increased. That means delta V mixing will be positive. And that is why the heat energy also increase. That is why delta H will be also increased. Okay, so what are the characteristics of positive deviation showing solutions are? PA is greater than P0 AXA. We know according to Rolle's law, PA equal to P0 AXA. They are deviating with the positive deviation is there. So PA is greater than P0 AXA, and PB, if the B component PB is greater than P0 BXB. That means for each component A or B, they are having their individual partial pressure will be more than we expected by the Rolle's law. Okay. Then delta H mixing equal to positive, delta B mixing equal to positive. That means volume of solution formed will be greater than volume of A plus volume of B. Okay. Example for this type of solutions are acetone plus ethanol, acetone plus carbon disulfide, water plus methanol, water plus ethanol, carbon tetrachloride, toluene, etc. are the examples. Next is the graphical representation. Okay, same thing like here in this axis vapor pressure. Okay, vapor pressure, and in this axis it is mole fraction. So I am taking XA equal to any component, you can take 0 here. Okay, XA equal to 0, then XB will be equal to 1. That is why it is marked mole fraction. Here you can see 0.2, 0.4, 0.6, 0.8, and maximum is 1. In the beginning it is 0. Okay. Okay, here mole fraction from this side it is increasing, that is XA was 0, it's become 1 here, that is increasing. Okay, that is why the arrow mark is pointed towards here. And here XP is this side it is pointed, that means it is increasing here because it was here 0 and it is become 1. Okay, so the normal we know ideal solution it was like this, and this one was like this for which one? This is for PA and this is for PB, it was like that, and one plain for total it was there. But positive deviation means same graph you have to draw, and here for total we have to write positive curve. That's the upper curve. Then here this is the normal line for the ideal. So here it is the positive one upper curve. Okay. So this is for which one? It was given for this one. This was for PB now. PB. That means for partial pressure of B component, this is the line. So on top you have to write the positive curve. Okay. So normal graph we have to draw for the ideal solution. Then we have to, what we have to do? Positive curve we have to draw. That is, this is the normal, this one. So suppose this is the one curve and second curve this is for the total. So total we have to positive curve, and here also one curve, and here also one curve. So that is the graphical representation. This is also very important. Okay. So next term is, one term you have to know in this positive deviation, that is azeotropic mixture or constant boiling mixture. What is the term? Azeotropic mixture or constant boiling mixture. Okay. So the mixture that distills, we know distillation, the mixture that distills without changing its composition is known as what? Azeotropic mixture. Okay. Suppose a mixture contains 20% water and 80% ethanol. That mixture, it boils or distills without changing that composition, 20-80%. Okay, that mixture is known as what? Azeotropic mixture. Okay, example for azeotropic mixture. It is very important. Okay, azeotropic mixture is two types is there, that is minimum boiling azeotrope is there and maximum boiling azeotrope is there. Okay, minimum boiling azeotrope and maximum boiling azeotrope. Okay, so what is minimum boiling azeotrope means? And a mixture and that shows large positive deviation from which one? Rolle's law. A solution or a mixture that show large positive deviation from Rolle's law is known as minimum boiling azeotrope, not maximum. Okay, large positive deviation showing azeotropic mixture is known as what? Minimum boiling azeotrope. Example for minimum boiling azeotrope is when if a mixture of if you are doing the fraction distillation of a mixture of ethanol and water. What is it? If you are doing the fraction distillation for a mixture of ethanol and water. Okay, So after sometimes we get a composition containing 95% by ethanol. That means it containing 95% ethanol and remaining 5% water. Okay, it's exactly given in the book 95.6. Okay, so approximately I'm taking 95% ethanol and remaining 5% water. That mixture is known as example for which one? Minimum boiling azeotrope. That means if we got that composition, okay, after we are how much we are heating or distilling or anything if you are doing, the composition of 95 and 5%, 95.6% ethanol and remaining percentage of water will be same in which phase? Vapor phase and in which phase? Liquid phase. That means that composition, it cannot change how much we are doing distillation or boiling. Okay, so azeotropic mixture means that is a graphically it is given here. So this classwork book clearly it is given. Just type here it was 100 water, 0 ethanol. Here it is 100 ethanol and 0 water. So after some time this is the liquid curve and this is the vapor curve. Okay. So here you can see this is the one point here you can see that point what is forming azeotropic mixture that containing 95.6% of ethanol and remaining water. Okay, so that is 4.4% water. Okay, so azeotropic mixture means that mixture that distills without changing their composition are known as azeotropic mixture, and there are two types of azeotropic mixture: minimum boiling azeotrope and maximum boiling azeotrope. Minimum boiling azeotrope means that shows large positive deviation from which one? Rolle's law. Example for that is 95.6% ethanol and water. Okay, so that is the which one here? Positive solution showing positive deviation and azeotropic mixture. Clear all of you, and this graphical representation is also very important. Next is non-ideal solution with the negative deviation. Okay, so it is opposite, everything is opposite to the positive deviation. Okay, so in this case the total vapor pressure of the solution will be less than that of an ideal solution for the same composition. Positive deviation it was greater than that of an ideal solution with the same composition. So vapor pressure of a solution will be less than that of an ideal solution with the same composition. Okay, so in this case the partial pressure of components A and B, suppose A is the solvent and B, the partial pressure of the components will be less than that calculated according to the Rolle's law. Okay, so why in this case, in this type of solutions, the boiling point will be greater, boiling point will be greater than that of the ideal solution. What is the reason why they are having the total vapor pressure is less, or why they are showing negative deviation? Means I explained already in case of positive deviation. In solution, AB force of interaction, that means solvent solute interaction is stronger than in solvent interaction and solute interaction. Okay, so in positive deviation AB interaction was weaker, so it was easy to break that bond. But in this case negative deviation, the AB force of attraction or interactive force between AB solvent and solute in the solution is greater than that in solvent and solute interaction. So what is the thing? So it is not easy to escape the molecules in the from the solution to the vapor state, because we have to supply more heat energy or energy to break this bond in the solution. So there is the vapor, which is not easy to go to the vapor state in the molecule. So that is why the vapor pressure will be decreases. That leads to which one? Negative deviation. So what is the reason? In solution, the interactive force between the solvent solute interactive force is greater than that in the pure solvent and pure solute. Okay, so it is not easy to escape the molecules to the vapor state. So that is why vapor pressure decreases, and this show which one? The negative deviation. That's why they are showing the negative deviation. Then how we can write the characteristics of this negative deviation solution showing negative deviation? PA, partial pressure of AA will be less than P0A XA. And for component B, PB will be less than P0A XB. In case of positive, it was greater than. Okay. Then delta H mixing is less than 0. In that case, it was greater than 0. Then delta B mixing is also less than 0. That means V solution V solution is less than VA plus VB. Volume of A plus volume of B will be less than which one? Volume of solution. Okay. Next is the graphical representation. This characteristics, they will ask minimum 3 characteristics of which one? Ideal solution, non-ideal solution with positive, and non-ideal solution with the negative deviation, and also the graphical representation. It's very easy, the graphical representation. Same thing we have to draw. Here which one was there? 0, 0.2, 0.4, 0.6, 0.8 and 1. This is mole fraction in this axis. Mole fraction. Okay, here I am taking XA equal to 0 and XB equal to 1. So here XA will be increasing this side. Here what will be there? XA 0 to it will become XA equal to 1. Here it was 1. So XB become 0 in this side. So we can show XB is increasing in this axis. Same thing. Okay. Here it is vapor pressure. Vapor pressure. Okay, so here it was XA, right? XB equal to 1 here. So it is maximum here. So it will be in decreasing like this. So this is for which one? PB. This is a partial pressure of BB. And here it was XA is the maximum. Okay, and here XA was 0. Okay, so it may be increasing from here to here. Or we can show XA was maximum, so it is decreasing. Anyway, you can see. So this is PA I am writing, and this is the which one? Total pressure. Right. Okay. So negative positive deviation means positive curve we were doing. For negative deviation, what we have to do? For each one we have to draw a negative curve. Means downward curve. Okay. So this is for which one? P total. Yeah, right. So this is, we can write it as PA. And this is, we can write it as PB. Okay. So that is the graphical representation. Positive means upward curve. Negative means which one? The downward curve. Okay. Then next is, I already told you, azeotropic mixture. In positive deviation, it was what? Large positive deviation showing was minimum boiling azeotrope. Here, if an azeotropic mixture that show large negative deviation is known as what? Maximum boiling azeotrope. If it is showing a large positive deviation, it is known as minimum boiling azeotrope. If it is showing a large negative deviation, it is known as what? Maximum boiling azeotrope. For example, it was given a mixture of 68% of nitric acid HNO3, okay, plus remaining 32% water, right? Okay, so a mixture that containing 68% of nitric acid and 38% water is example for which one? Maximum boiling azeotrope. Okay, simply I will draw the graph. Okay, so it was like this. Okay, it will come, and this is the and here also it will come like this. I am not showing exactly, I am drawing just to show. Here it was 100% water, here it was so 0% HNO3. So here it is 100% HNO3 and here it is 0% water, like that. Okay, so it is not the exact curve, simply I am showing. So here the one point it is reached, we will get the azeotropic mixture. That means it is containing 68% HNO3 and the 32% what is there? Our water. Okay, and the temperature corresponding to this is 120.5 degrees Celsius. Okay, In that ethanol and water mixture, that's minimum boiling azeotrope, it was 78.5 degrees Celsius. We got that azeotropic mixture. So that was low temperature. That's a minimum boiling we can call. Here it is getting around 120.5 degrees Celsius. That is the high temperature compared to the other one. So we can call it as maximum boiling azeotrope. Okay, so example for minimum boiling azeotrope and example for maximum boiling azeotrope you have to know. Okay. Then example for positive, the solution showing positive deviation is, many examples are given in the classwork. That is acetone plus aniline, acetone plus chloroform, ethanol plus acetic acid, then water plus nitric acid, etc. are given. So clearly it is given the examples in the notes. Okay, so you can learn that one. The next is coming the difference between ideal solution and non-ideal solution, then the difference between the solution showing positive deviation and negative deviation. So everything we explained clearly, so that differences it is clearly given in notes. Okay, so you have to learn that one. Okay, so that's about today's class. Thank you girls.